In this video, we're going to be talking about oxygen production on the moon, why it matters, and how it can be done. First thing to recognize is that large rockets are extremely thirsty for oxygen. A Falcon 9 can use 300 tons of oxygen to get to orbit, while Starship uses 4,000 tons of oxygen. Now, there is a difference whether these rockets are set up in expendable or reusable mode, but in any case, it's tons and tons of oxygen. There's three main types of rocket engines, and the main stage rockets are typically liquid combustion rockets, which means they use liquid fuel and liquid oxygen. And in terms of the composition of that propellant, it's majoritarily oxygen, 70 to 90% oxygen by mass. In terms of the fuels, typical ones would be hydrogen, methane, kerosene, ethanol, and also in the past, methanol. To help gain a little bit of an intuition around this oxygen to fuel ratio, it can help to look at the chemical reactions. So for methane combustion, we need 64 grams of oxygen for every 16 grams of methane. So 4-to-1 oxygen to fuel ratio. And for hydrogen combustion, it's 32 grams of oxygen for every 4 grams of hydrogen. So a 9-to-1 O2 to fuel ratio. And that's partially because hydrogen is such a light molecule. On Earth, we take oxygen for granted. It's 21% of the atmosphere. It's always around us, available for our engines, other than rocket engines, which consume way more oxygen than would be available in a large volume of air nearby. But typically, there's always oxygen abundantly available around us. But what about in space? Clearly, combustion engines will not be able to depend on the vacuum of space for their oxygen supply. And on top of that, let's say we want to refuel ships at space stations, we're going to need an oxygen supply chain. So the oxygen could come from Earth, but maybe the moon can help. And indeed, that is one of the reasons why there's so much going on with lunar exploration these days. There's a number of private companies, there's the public space agencies, and there's these two flagship projects, the Artemis missions and the International Lunar Research Station. In terms of the private companies, we've seen a mixed bag of results. There's been a number of failures, some semi-successful missions, and also at least one fully successful mission. But what's more important is there's a ton of missions coming up in the next few years from these private companies and from others. And on top of just, sending lunar landers and rovers to the moon, a lot of these companies are partnering with organizations or developing themselves technologies to extract oxygen from the moon, which we'll get into later in the video. At the same time, there's a lot going on with the public space agencies that are just maintaining and increasing the cadence of missions to the moon, deploying satellites, deploying rovers, deploying landers, testing out new infrastructure for developing a more self-sufficient lunar economy. A lot of the interest in the moon comes down to its shallow gravity well. When we carry mass from Earth into space, it's a really tough battle against Earth's deep gravity well. So ideally, we would only carry essential things from Earth, like people and high-value cargo. For commodities like metals and oxygen, if those can be sourced from shallow gravity wells for the space economy, they could be a great benefit to the space logistics. When we launch a rocket from Earth, it's less than 5% payload and over 95% propellant. Actually, we're using a lot of fuel just to lift that fuel as well. When we launch a rocket from the moon, it could be upwards of 25% payload. Again, that's because of Earth's 1/6 g gravity and also its lack of atmosphere, which reduces friction. Let's imagine that there was a space station at Earth Moon Lagrange point 1, and we wanted to supply that space station with propellant. Well, if we were to launch rockets from Earth to that space station, we would burn 25 kilograms propellant in order to carry 1 kilogram of payload, in this case, also propellant, on a one-way trip. On the other hand, if we were using the moon as a supply source, we would burn only 4 kilograms propellant to get 1 kilogram of payload, and that would be for a round trip, meaning the rocket could come back down to the moon. So that means that the economics of supplying from the moon look potentially attractive from this perspective. Now let's put all this in the context of Mars colonization. So of course the space agencies and SpaceX have plans to go to Mars. SpaceX has a particularly ambitious plan of putting 1 million people into a permanent city on Mars in as short a time as possible. Their current architecture looks like this. They're planning to launch 10 starships where the payload of these starships is actually propellant. They're going to launch these into orbit and they're going to refuel a single starship so that it's ready to make the journey to Mars. And that single starship will be carrying 100 people and probably some critical equipment to, make that colony on Mars. So that ship goes to Mars, and when we think about scaling this up now to 1 million people, we're going to need 10,000 of these Mars-bound ships. We're going to need 100,000 of the launches from Earth to resupply the propellant. So that's a total of 110,000 launches from Earth to get 1 million people to Mars. At 10 launches per day, this would take about 30 years, which is a very long time. And also, it's not really clear that we could do 10 launches per day. We don't really have the facilities for this at the moment. So there might be a better way. On top of this, there would be a fair bit of CO2 emissions. And also, scientists have speculated that the ozone damage caused by this many launches could start to take a toll. So, is there an alternative solution to this plan? So, this is where the moon comes into play. We could build lunar infrastructure for oxygen production. And then we would take advantage of the moon's shallow gravity well, its lack of atmosphere, which give these payload ratio benefits to make a supply chain from the lunar surface to carry oxygen to a fuel depot at Earth Moon Lagrange point 1. And then ships that are destined for Mars from Earth would carry only people and critical supplies. And importantly, they would have the minimum propellant required just to reach that fuel depot where they would refuel. So now, when we think about colonizing with 1 million people, the space logistics look quite different. We still need the 10,000 launches from Earth with 100 people, that's unavoidable, but we completely get rid of this 100,000 starships from Earth for propellant. So that could be, for example, a benefit for the ozone issue that we mentioned. On the other hand, we need infrastructure launches. We need launches to build that moon infrastructure. So then the question comes, is it worth investing in lunar infrastructure for auction? Well, it depends on the lunar infrastructure required and the efficiency of production and so many of these types of questions. And another caveat we have to consider is that we also need fuel on the moon. We need that reducing agent, either hydrogen, methane, or something else. And it's not really currently available on the moon in large quantities because, unlike Earth, there's no fossil fuels on the moon. So hydrogen could be produced from water, but there's no methane available. In this video, we looked at the basic foundations for the lunar oxygen argument, and in subsequent videos, I'd like to dive into the next big questions. For example, how can oxygen be produced on the moon? Which forms is that oxygen in? Which locations is it in? What technologies are available? And who are the key players developing those technologies? Also, is it economically viable? What are the yields, the efficiencies? And one of the key pieces of the puzzle that I've studied quite a bit is the energy required for oxygen production on the lunar surface. And I published a study with the European Space Agency this year on this topic. So I'll be explaining how we did our work, how we did our research, and what were the results of our study.